In this session, we discuss about received signal power with respect to noise power. Here we are starting from the calculation of a range equations. The main purpose of a link budget to verify the communication system will operate according to the plan. That is, the message quality, error performance will meet these specifications or not. The link budget monitors the up and downs of the transmitted signal from its inception at the transmitter until ultimately received by the receiver. The complication else how much of signal to noise ratio received and how much of safety margin exits beyond when it is required. The process starts with the range equations, which relatives power received to the distance between transmitter and receiver, and we develop a range equations. In the radio communication, the carrier is propagated from transmitter by the use of transmitting antenna. The transmitting antenna is a transducer to convert electrical signal into electromagnetic fields. Already we discussed in previous video. As a receiver, the receiving performs the reverse function. It converts EM fields into electrical signals. The development of fundamental power relationship between the transmitter and receiver usually begins the assumption of monodirectional RF sources. There is a two types of RF sources we have. One is the directional sources, second one is the omnidirectional sources. So directional sources like as a directional antenna which propagate the radiation beam on specific direction, but omnidirectional sources which spread the field in all directions, that is 360 degrees direction, that 4 pi with a 4 pi steradians, such as ideal sources called as a isotropic radiators. So here we discuss about the isotropic radiators which spread the particular field in 4 pi steradians, or we can be called as a 360 degrees variation. The power density P of D on a hypothetical sphere at a distance of D from the source is related to the transmitted power PT. PT is a transmitting power that can be delivered by the transmitting antenna. Based upon the value of PT, we calculate the value of power density P of D, that is equal to PT divided by 4 pi D square, or in terms of a R, this is called PT divided by 4 pi R square if R equal to D. Since 4 pi D square is the area of the sphere, the power extracted with the receiving antenna also we can be written as P received is the multiplication of power density is multiplied by effective area of an antenna, that is equal to PT into effective area of the antenna, that can be divided by 4 pi D square or 4 pi R square. So now the received power will changes into PD AER divided by 4 pi R square, where AER is the effective area of antenna, is the ratio between total power extracted by the incident power flux density. It is also called as absorption cross sectional area of receiving antenna. Once again I repeat, here we calculate the value of power density, that is P of D, that is equal to PT divided by 4 pi R square, and after that we are calculate received power is the multiplication of a power density is multiplied by the effective area of antenna, that is PT is multiplied by effective area of the antenna is whole divided by 4 pi r square. If the distance is d, the above equation can be also written as Pt multiplication by effective area of antenna is whole by 4 pi d square. Both are similar equations. In the figure, we can observe that we are placing one particular isotropic radiator at a point Pt, and we are observe what is the power density at a point outer circle. So we can be notice that here there is a one point, and the spacing between these 2 points we have to consider as a d or r. Based upon all considerations, we can be write the equation for Pr, that is Pt into Aer divided by 4 pi r square. Now antenna efficiency and gain calculation. If the antenna is under consideration of the transmitting antenna, the effective area is designated by AET. If the antenna in question is specific as to receive or transmitting function, the effective area can be designated simply AE. An antenna effective area AE and physical area AP are related by the efficiency parameter eta, that is equal to AE by AP. AE by AP. Based upon these, we accounts for the fact of total incident power is not extracted. It is the loss of variation mechanism. Nominal value of eta are 0.55 for the parabolic and shaped reflector, and it is 0.5 for hard shaped antennas. That means based upon antenna effective aperture or physical aperture, the value of eta is varying from 0.55 to 0.75 or some other value. Based upon these values, the antenna parameter that related to the power output to an isotropic radiator as a purely geometric ratio of the antenna directivity or directive gain. We can be called as a antenna gain or can be called as a directive gain. So directive gain is the ratio between maximum power intensity divided by average power overall 4 pi steradians. In the absence of any loss or impedance mismatch loss, the antenna gain is defined simply as the directive gain. However, in the event there is existing some dispersive and impedance mismatches losses, the antenna gain is equal to the directive gain times of loss factor to account of these losses. Here we shall assume that the dispersive losses is 0 and the impedance is perfectly matched. Therefore, described peak antenna gain can be viewed as the resultant of concentrating of RF flux in some restricted region less than 4 pi steradians. Now we can see in defined effective radiation power with respect to isotropic radiator, we can be called EIRP, as a product of transmitting power PT and the gain of transmitting gain GT. In the figure, we observe that there is a one antenna which radiate the particular radiation one undefined direction. Every antenna is having three types of lobes. First one is main lobe, second one is minor lobes, and the third one is back lobe. A main lobe can be considered as in the direction of maximum gain direction, and a minor lobe can be considered as less gain direction. It is attached to the main lobe, and there is some lobes are existing depend upon the antenna type. There is a back lobes. If you decrease the intensity of the back lobe and side lobe, proportionally there is a increment of a gain of major lobe. Why? Because what we are transmitting the power by the transmitting antenna will be adjustable to all these type of lobes. If you compress one type of a low power, automatically the power will be delivered to the remaining more lobes existing in the antenna. Here we observe there is a peak, that is minus 3 dB peak, and one more peak output power of EM feet, and shown of antenna side lobes and transmitting antenna and antenna main lobes. Based on power transmitting and gain, the isotropic radiator EIRP is defined as product of transmitting power and gain. Again back to the range equation, for the more general case in which the transmitting has some antenna gain relative to the isotropic antenna, we place the value of a PT with EIRP equation, it changes into received power is equal to EIRP is multiplied by effective area of antenna divided by 4 pi r square. The relationship between antenna gain and effective area can be taken as Z is equal to 4 pi AE by lambda square. 4 pi AE by lambda square. Based upon all these, we can be transfer a new power receiving formula. In gain, G is equal to 4 pi AE by lambda square, where lambda is the wavelength and F is the frequency of reciprocity, and lambda equal to C by F, and C is speed of a light. So before derivating the received power, we have to calculate effective isotropic radiated power with some example. Show that same value of EIRP can be produced equally well by using transmitter with a transmitting power is 100 watts or with a transmitting power is 0.1, employing the appropriate antenna in each case. Coming to the solution, we have seen in the above figure, 100 watts of a transmitting coupled with an isotropic antenna, the IIRP is equal to multiplied by power with respect to gain, that is 100 into 1, that is 100 watts. And 0.1 transmitting coupled an antenna with a gain GT is equal to 1000, and EIRP is approximately equal to 0.1 is multiplied by 1000 is 100 watts. If a field strength meter was positioned to measure the effective power and the measure could not be distinguished between these two cases, that means the EIRP is directly proportional to the gain observed by the antenna or gain generated by the antenna and receiving power. If both are maximum, proportionally you will get the effective isotropic radiated power EIRP is also a maximum. If the receiving power will reduces, it is effect on the EIRP which is existing on the antenna. Now coming to the range equation. For antennas, we already discussed that the gain is equal to 4 pi is multiplied by effective area of the antenna divided by lambda square. Now that is equal to 4 pi effective area, lambda is replaced by C by F, that is equal to F square by C square. Now the resultant equation Z is equal to 4 pi effective area is multiplied by F square divided by C square. The antenna fields of view is a measure of solid angle into which most of fields power concentrated. Field of view is a measure of directional properties of an antenna. It is inversely related to the antenna gain. Gain of antennas are commensurate with narrow fields of view. Instead of using solid angle field of view, we often deal with planar angle beamwidth measure. in radians and degrees. The beam width is the angle of subtend of position with the peak fields is reduced by 3 dB. How does the antenna beam vary with the signal frequency? How does the beam width vary with the antenna size? As we can see in the above equation. The antenna gain with decreasing wavelength, antenna gain is also increasing with increasing of effective area. Increasing of effective gain is tantamount of focusing the flux decrease into a more restricted cone angle. Hence, increase either by signal frequency of an antenna sizes results narrow beam width. If you consider the effective area with gain is equal to 1, then that is equal to lambda square by 4 pi. That means the value of a GR is equal to 1. GR is equal to 1. According to the antenna reciprocity, for a given antenna and carrier wavelength, the transmitting and receiving antennas are identical. Again I repeat, based upon the antenna reciprocity, for a given antenna and carrier wavelength, the transmitting and receiving antennas are identical. So, the value of a GR that is equal to 1, that is equal to 4 pi, effective area is divided by lambda square. Now, effective area is equal to lambda square by 4 pi and it can express it as C square by 4 pi into F square. Then we calculate the finding receiving power with the receiving antenna is isotropic. We substitute the above equations. Now the received power is equal to EIRP multiplied by effective area divided by 4 pi r square. Now the received power is equal to EIRP into lambda square divided by 4 pi whole square into r square. Why? Because we replace the effective area by lambda square by r square for a gain is equal to 1. Now that is equal to EIRP divided by 4 pi r divided by lambda whole square. Now that is equal to EIRP divided by LS, where the collection of terms 4 pi by d lambda is called as a path loss or free space loss is designated by LS. In the above equation states that the power received by an isotropic antenna is equal to the effective transmitter power reduced by only the path loss. When the receiving antenna is not isotropic, replacing effective area with G is equal to effective area in the equation Z lambda square by 4 pi. It adds a new expression that is receiving power P is equal to EIRP G lambda square by 4 pi r whole square, that is equal to EIRP GR by LS. That implies if we consider gain is equal to 1, the received power is equal to EIRP divided by path loss. If you are consider it is not isotropic antenna, P received is equal to EIRP divided by LS is multiplied by G, where LS is called as a free space loss or path loss, and it can be expressed as LS is equal to, in terms of a R and lambda, LS is equal to 4 pi into R divided by lambda whole square, that is equal to 4 pi R F by C whole square. And we know that antenna beam width, since it is an isotropic antenna, is defined a gain of 1. The area ratio of antenna beam pattern from the maximum of minus 3 dB to area of the sphere is often an estimate over a antenna gain. For an antenna gain with off power beam widths into two planes with a directivity D is given as G is equal to D is equal to 4 pi by theta x dot multiplied by theta y. For pi by 4 beam, G is equal to, or directivity is equal to 4 pi divided by pi by 4 multiplication by pi by 4, that is equal to 4 cube divided by 5, that is approximately equal to 20.37. Based on all these expressions, we can be write the Fourier transmission equation or range equation, that is the received power is equal to EIRP divided by LS into G, that is equal to PT into GT into GR whole divided by 4 pi R by lambda whole square. Now it can be rearranged with a family relationship with respect to PR and PT. PR is equal to PT multiplied by G and effective area whole divided by 4 pi R square. That implies PT AE into GT GR divided by 4 pi R square. That implies PR is equal to PT multiplication of effective area of the transmitter and effective area of the receiver whole divided by lambda square into R square. That implies PT into multiplication of effective area into effective area of the transmitter and effective area of the receiver whole divided by C by F whole square into R square. Now if you consider the path loss considerations, path loss is defined as using the isotropic receiving antenna, that is 4 pi r by lambda whole square, that is equal to 4 pi r f by c whole square. And the received flux density is strictly as a function of distance, that is power density is equal to EIRP divided by 4 pi r square. And the large effective area of the receiving antenna is expressed as EIRP into effective area divided by 4 pi r square. Based on all these equations, we can conclude that the receiving power with respect to gain is equal to PT into GT into GR into lambda square by 4 pi r whole square. In the above equation, AER and AEF are the effective area of the receiver and the transmitter. The dependent variables of the receiving power PR, the independent variable involves the parameters such as transmitting power, antenna gain, antenna area, wavelength and the range. Suppose we ask the question, how does the receiving power vary wavelength is decrease or increase? All other independent variables are remaining constants. It appears that the receiving power and wavelength are not related to all. From the above equation, PR appears to be inversely proportional to the wavelength squared, and also PR appears directly proportional to the wavelength squared. Is there paradox here? Yes, of course there is not. Equation seems to be constant only because antenna gain and antenna area wavelength are stated in the equations. We should one of these equations for determining of receiving power as a function of wavelength. Considering a system already configured, there is the antennas have been built, other dimensions are fixed. The equations is appropriate choice to calculating the receiving power performance for a fixed size of antennas, and the receiving power increases, wavelength goes on decreases. Consider in the equations the gain and effective area independent variables. We want to gain and effective area of the receiver held fixed over a range of receiving power versus wavelength calculations. What happened to the gain for a fixed dimensions transmitting antenna and the independent variable of lambda is decreases? When gain is increases, but we cannot have gain is increases. We want to gain has to be fixed. In other words, to ensure that gain remains fixed, we need to reduce the transmitting antenna size and wavelength decreases. It should be appearing in the equations. For a fixed transmitting antenna gain requirement and the parameter of effective area is not fixed. For similar reasons, the effective area gain are fixed. In the equations is used to both transmitting and receiving gains are fixed values. The figure explains the state application of satellite where the downlink of antenna beam is required to provide earth coverage. beam approximately 17 degrees from the synchronous altitude. Since the satellite gain G must be fixed, the resultant PR independent on the wavelength shown in above equation. If the transmission line some function of F1 provides earth coverage, the frequency changes to F2 where F2 is greater than F1 will result the reduced coverage. Hence, antenna size must be reduced to maintain required earth coverage of B. This earth coverage antenna becomes smaller as the carrier frequency increases. As in the above equation, it can be seen that LS is the path loss, is wavelength frequency dependent. The question is often asked, why should the path loss, which is just a geometric inverse squares loss, be a function of frequency? The answer is, the path law is characterized as a definition predicted onto use an isotropic antenna gain is equal to 1. Hence, the path loss is convenient tool. It represents a hypothetical received power loss that would be occur if the receiving antenna were isotropic. The above equations are established the power density of P of t as a function of distance and purely geometric considerations. P of d is not a function of frequency. However, since path loss is predicted on Gr is equal to 1, when we attempt to collect some pairs with isotropic antenna, the result is characterized by above equations. Again, let us emphasize the path loss can be viewed as a convenient collection to term have been assigned to fortunate name as a path loss. The name conjures up an image of purely geometric effect and fails to emphasize the requirement of gain as a unity. A better choice a name would have been unity gain propagation loss. In a radio communication system, the path loss accounts for the largest loss in a signal power. In a satellite systems, the path loss of a C-band of 6 GHz link synchronous altitude satellite is typically 200 dB. Now let us consider example from the textbook which we discussed previously. Design a hypothetical experimental measure of a path loss with a frequency of F1 is equal to 30 MHz and F2 is equal to 60 MHz when the distance between transmitter and the receiver is equal to 100 kilometers. Find the effective area of the receiving antenna and calculate the path loss in decibels for each case. We have two cases. One is F1 at 30 MHz and F2 is equal to 60 MHz. We have to find path loss for each and every case. We know that from the above equation, two links of frequencies F1 and F2 respectively Now we have to calculate the power density, that is equal to EIRP divided by 4 pi d whole square. This reduction of a power density is due to only the inverse square law. The actual power received at each receiver is found to be multiplying the power density at a receiver by effective area. Now effective area of the all collecting antennas shown in the equations, since the path loss is predicted on G is equal to 1, that is isotropic antenna. We compute first effective area at frequencies f1 and effective area of the receiver at frequency f2 by the equations. We know that effective area is equal to lambda square by 4 phi if gain is equal to 1. If there is a gain is existence, effective area is equal to G into lambda square by 4 pi. But we consider it is isotropic receiver, so that's why G is equal to 1. So proportionally effective area of the receiver is equal to lambda by f whole square divided by 4 pi. That implies 3 into 10 power of 8 by operating frequency in the first case, that is the 30 megahertz, that is 30 into 10 power of 6 whole divided by 4 pi. That results 8 meters square is the effective area of the first case. And similarly effective area of the second case, that is at the frequency of 60 megahertz, we produce 2 meters square. And we find the path loss of each in decibel. Ls is equal to 10 into logarithmic of 4 pi d lambda 1 whole square. That implies 10 into logarithmic of 4 pi into d is 100 kilometers they are given, that is 100 into 10 cube, that is 10 power of 5 whole divided by lambda c by f, that is 3 to 10 power of 8 divided by its frequency, that produce 102 dB. And see the process in the case number 1, the EIRP from the transmitter to receiver with a distance with respect to receiver gain is equal to 1. And in the case 2, if f2 is greater than f1, initially we have take the case 1 as a 30 megahertz. For the case 2 is f2 is equal to 60 megahertz. Then f1 is less than the value of f2. In the both two cases, in the case number 1 we fix the value of f1, and the case number 2 we are fix the value of f2 as a 60 megahertz. Based upon all these parameters, we calculate the value of a receiving power. EIRP is multiplied by effective area whole divided by 4 pi d whole square. And we observe that in the two cases there is some relation, that is f2 is greater than f1. For the case number 2, we will observe the path loss is equal to 108 dB. For the case number 1, we are observed the path loss is equal to 102 dB. That means if the particular range of frequency is goes on increases, that means 30 megahertz to 60 megahertz, proportionally the path loss is goes on increases. In this case number 1 having 102 dB approximately, but in the case number 2 where the frequency is f2 is greater than f1, the particular path loss is increases to the 108 dB. So that will be explained in this figure. If the frequency is 3 kHz, that is 3 into 10 cube, that is minus 18.02 dB. If the frequency is 10 power of 6, that is increased to 41.98 dB. If the frequency is 10 power of 9 gigahertz, that is 3 gigahertz, that is 101 into 98 dB. That means the path loss is always proportional to the frequency of operating of the system. If the frequency of the operating of the system is increases to f1 to f2 or f2 to f3, and proportionally the value of a path loss is goes on increases. In order to explain the example, in order to explain the particular analysis, we consider this example as a reference. Now we discuss thermal noise power. Thermal noise power caused by the thermal motions of electrons in all conductors. It is generated by the lossy coupling between the antenna and receiver. And in the first stages of the receiver power spectral density of a constant of all frequencies up to 10 to the power of 12 Hz, giving rise the name of white noise. The thermal noise processing in communication receiver is modeled as an adaptive white Gaussian noise process. The physical model for the thermal noise or Johnson noise is a noise generator with a open circuit mean square voltage, that is 4K temperature multiplied by W into R, where K is the Boltzmann constant T is the temperature is under Kelvin, and W is the bandwidth hertz, and R is the resistance ohms. Based on all this, the maximum thermal noise N could be coupled from the noise generator in front of end of the amplifier. That is N is equal to K T naught into watts. The maximum sideband noise power spectral density N naught available at an amplifier input N naught is equal to N naught by W, that is equal to K into T naught watts per Hz. It might be seems the noise power should depends on magnitude of the resistance, but it doesn't not. Consider an argument with verify this. Electrically connect a large resistance to small one such that they are from closed path and such that their physically temperature are the same. If the noise power were as a function of resistance, there would be a net power flow from the large resistance to the small resistance 1. The large resistance would become cooler and small one would become warmer. The words for experience not mentioned in the second law of thermodynamics. Therefore, the power delivered from the large resistance to small one must be equal to power it's received. The available power at the thermal noise source is independent on the ambient temperature of the source, that is the noise temperature. The sleeps help the concept of effective noise temperature for the noise sources. They are not necessarily thermally in origin that can be introduced into the receiving antenna. The effective noise temperature of such a noise sources is defined as the temperature of hypothetical thermal noise sources that would rise to equivalent amount of interfering power. It will be discussed in next chapters. Now we discuss one particular example to enhance the maximum available noise power by considering of one example. Now let us take an example. Using a noise generator with a mean square voltage is equal to 4K temperature WR. Demonstrate the maximum amount of noise power that can be coupled from the source into a amplifier with input noise is equal to K T naught into W. As the theorem work for the network theory states that the maximum power will be delivered to the load when the value of a load impedance is made equal to the complex conjugate of the generator impedance. In this case, the generator impedance is a pure resistance R. Therefore, the condition for the maximum power transfer is fulfilled when the input resistance and amplifier equal to R is shown in the below figure. It explains that the input thermal noise is represented by the electrical equivalent model consisting a noiseless sources resistance in the series with the ideal voltage generator, whose RMS voltage is equal to square root of 4K temperature WR. The input resistance of the amplifier made equal to resistance R. The noise voltage delivered amplifier input just half of the generator voltage. Follow the basic circuit properties. The noise power delivered to the amplifier input can be according to expressed as Ni is equal to square root of 4K temperature WR by 2 whole square divided by R. That implies 4K temperature WR divided by 4R, that is equal to K T naught into W. It is expressed in the below figure electrical mode of maximum power transmission thermal noise power amplifier input. See the structure, we can observe how the power will be delivered from the source to load. And we've seen some of the radio receiver considerations. Receiver collect the signals, interference and losses. Signals of interest will require the gain and filtering period as a part of signal processing. The noise collected by the receiver will processing along with the signal but will limited by the filtering, and the electrical components will add their own noise to the processing of signals. Therefore, we need to discuss again cascade of gain signals, cascade of noise effects and the component noise figures. bandwidth effect on the thermal noise power in the next coming sessions. And one more RFID receiver down conversion. So this is a simple down conversion or RFID receiver. So here we are receiving the signal with a high pass filter with a carrier frequency of 915 MHz. Then it will be moved to the synthesizer and with a carrier frequency of a 140 MHz with IF filtering. Then a fixed oscillator, local oscillator, it will be processed with a 152.5 MHz and it will be given to the low pass filter with carrier frequency of a 12.5 MHz and finally do the analog to digital conversion. It is a simple down conversion. Here we are using ISM band for down conversion of 90 to 928 MHz and high side line of sight and IF filter sideband and LPF for the analog to digital anti-aliasing and conversion of a FS by 4 post analog to digital conversion complex processing. And finally, we have to discuss a simple topic, that is the cascade gain. So cascade gain, name itself indicates it is a mixing of different values of gains, in different stages. Multiple in a gain for each stage. If the gain is dB, if add the gains and subtract the losses, that is gain is total under dB is equal to generated by the RF, generated by the mixer, generated by the IF stage and generated by the, if there is any second mixer, and generated by the IF second stage. If the particular mixer having the loss instead of gain, and the overall gain can be expressed as gain generated by the RF minus L in the first mixer, loss in the first mixer in dB, plus gain in the second IF stage, first IF stage minus loss in the second mixer plus gain in the second IF stage. So that means if the particular gain is adding, it is moving on summation process. If the adding the losses with the down session, down conversion session, we subtract the losses. Linear in gain multiplication, gain dB in additive. Now we discuss some of the bits regarding about these topics. Now we discuss the bit number 1, which has some same power of spectral density. There is a white noise, brown noise, white and brown noise, and none of the above. Yes, answer is A. White noise has some power spectral density where it is decreases in case of a brown noise. We discuss in the next video. Coming to the next bit, the capacity of a channel can increase the channel bandwidth, increase the signal power, increase the channel bandwidth and signal power, and none of the above. Answer is C. Channel capacity increases by increasing the channel bandwidth and also increase by signal power. Very important bit. Keep it in mind. Channel capacity is increases by increasing of channel bandwidth and also increasing by signal power. If you increase the both two parameters, proportionally the channel capacity goes on increases. Coming to the next bit, capacity of the channel is increased by reducing the band noise power. If it is true or false, answer is A. True. Capacity of the channel can be increased by reducing in the band of noise power. Once again I repeat, capacity of the channel can be increased by reducing of the band noise power. That means in the previous bit we discussed about capacity of the channel increased by bandwidth along with the transmitting power, and capacity of the channel is also increased by reducing the band noise power, that is frequency noise power, noise generated by the frequency. Next point, noise as infinite energy, infinite power, infinite energy and power, none of the above. Answer is A. Noise is infinite energy signal. It is not a power signal. Make sure that very important bit. Noise is a energy signal, not a power signal. But it forming on infinite mode, not a finite mode. So that's why we can be consider every noise in the system may be generated in the signal as a energy signal, not a power signal. Coming to the next bit, thermal noise is A. Energy signal, B. Power signal, C. Energy and power signal, B. None of the above. Answer is thermal noise can be considered as a power signal and it is infinite energy. See the difference between previous bit and present bit. Here we discuss about the noise. Noise is infinite energy. Now coming to the present bit, thermal noise is a power signal but it has infinite energy. See this, thermal noise can be considered as a power signal but it has a infinite energy. Thermal noise is a noise, we have to consider as a power noise, but here noise are related to the signal noise, but signal noise has a infinite energy. It is also infinite energy, but we have to consider thermal noise as a power signal, not a energy signal. Coming to the next bit, thermal noise is a wide sense stationary process. It can be expressed whether it is true or false. Yes, answer is true. Thermal noise is modeled as a wide stationary stochastic process. So that means thermal noise, that means noise added by the temperature either in the antenna or any block in the transmitter or receiver, we have to consider as a wide sense stationary process. So that's why temperature noise is modeled as a wide sense stationary stochastic process. Wide sense stationary stochastic process. Coming to the next bit, the maximum likelihood function is positive, negative, or any one of the mentioned and none of the above. Answer is always maximum likelihood function is a positive value. The maximum likelihood function is always positive. It cannot be considered as a negative. It cannot be considered as a negative. Coming to the next bit, matched filtering operation includes spectral phase matching, spectral amplitude matching, spectral phase and amplitude matching, none of the above. Yes, it is a spectral phase and amplitude matching. Matched filter includes two operations, spectral amplitude matching and spectral phase matching. We have to match with amplitude with respect to frequency level. We have to match the phase with respect to frequency level. So that's why matched filtering in the receiver side we are supposed to use. It can be including spectral amplitude matching and similarly spectral phase matching. Now coming to the next bit, matched filter is A. Linear, B. Non-linear, C. Linear and non-linear, and D is option is none of the above. Now the answer is matched filter is completely linear filter. It is not a not linear filter. It is not a non-linear filter. Such applications which are supposed to use linear, in that particular case we are use matched filter at the receiver to detect the noise analysis of the system. Now in these videos we are completely analysis in the system starting from the range equation. We are calculate the power density with respect to transmitting power and distance between the transmitting and reference point, and after that we are analysis the effective area of the aperture area of the receiving antenna based upon the total power and power flux density, and after that we are calculate the value of eta, that is efficiency parameter based upon the effective area and aperture area of the transmitting antenna, and after that we are finalize that the value of a gain. We identify that if a particular radiator is isotropic, we finalize that the gain is equal to unity. At the same time, if the antenna structure will be changes, the proportionally the value of efficiency also changes from 0.55 to 0.75 depend upon the shape. And also we analysis the lobes, main lobe, major lobe and back lobe in the antenna beam patterns, and we observe that we have to compress side lobes and back lobes in order to get the maximum gain and maximum directivity by the antenna. And we example EIRP of a particular value with by considering of one example, and in the example we consider two powers. One is at 100 watts and second one is at the 0.1 watt, and we estimate what is the value of a EIRP. And after that we have to estimate the value of a receivable power based upon the EIRP. And after that we are calculate the value of a receiving power relations with respect to gain, receiving power relation with respect to path loss, and receiving power relation with respect to EIRP. And finally we can conclude that the Phillips equation or the particular range equation PR is equal to PT into GT GR lambda square by 4 pi d whole square. And also we are confined different types of considerations relations between the receiving power, transmitting power, lambda with respect to distance. And after that we are estimate the path loss in frequency dependent by considering of one example. We are considering an example and considering one frequency at 30 MHz and one frequency at 60 MHz. We are calculate the value of a effective area and along with the path loss, and we make it as a table. In the table we can conclude that if the particular frequencies goes on increases, proportionally the path loss is affected. And finally in the session we discuss about thermal noise. The thermal noise we are estimate with some value of n by considering of Boltzmann constant, temperature and bandwidth along with the receiver resistance under ohms. And finally we can make a maximum available noise power by considering of maximum power transfer theorem. And we can discuss some of the examples and some of the optional bits which are related to the noises. Thank you.